That is what I'm doing from our last class. Okay, so for whatever I have covered, I am dealing simultaneously with the theory and also the software. Okay, which means you should know the concept of design. Okay, that is the aircraft design part. So here, being with different aerofoil addition. As we know, this is our wing, which we have already designed. That is a basic wing model I have shown you. But we haven't went for the complicated part, right? Why I have shown? Because just to give the idea about the wing and the aerofoil. Okay. Now in today's topic, we will go in deep about the wing with different aerofoil additions. As we know, here while designing basic wing model, we have used a particular aerofoil that is 2421, 4 series 2421. Like this only we have different aerofoils. So here, if I recap again the basic thing about the aerofoil, that is shape like this we have. Okay, why we don't go for other shape like this or circular shape? Why only aerofoil? Okay, maximum all our components. If you take the cross sections of our components, that will be in aerofoil shape only. Why? Because in this case, this type of design, what we have, aerofoil steam uh, kind of body. Okay, so this shape will give less drag as compared to the other shape what we have, the rectangular based or circular based. Okay, so as we know, if we keep on flat plate like this, okay, rectangular based plate, and if we send any flow, then of course this complete part it will resist. This part it will resist to that flow. Okay, where in this case 50% it will resist and 50% easily air will flow. But in this case, the drag will be only 5 to 15% drag will be there, and air will flow smoothly over the upper surface and lower surface, which means there will be no much drag in this aerofoil kind of shape. That's why maximum all the aero components will design in this kind of shape. Okay, that is aerofoil shape. So here aerofoil, that is the cross section. Okay, just let me select my mobile. Yeah. So here aerofoil, the definition of aerofoil, it says that the cross sectional shape obtained by the intersection of the wing with the perpendicular plane is called as an aerofoil. Okay, so here we suppose if we have a wing like this, the 3D wing. Okay, so if I cut this cross section, okay, like this, if I cut, then I will get this kind of 2D shape, right? So that is nothing but our aerofoil. Okay, here we have the wing. Okay, so the cross sectional shape what we will get, the shape, the cross sectional shape will get, okay, by intersection of the wing with the perpendicular plane. This is a perpendicular plane and this is our wing. Okay, the intersection between the wing and the perpendicular plane. Okay, if we cut, then we'll get the shape. That shape is called as the aerofoil shape. Okay, so here aerofoil shape, if we see, then see here we have the aerofoil shape for blade, which means if you take the cross section of this blade, then we can able to see the shape. It will be like aerofoil shape and aeroplane wing. Okay, like this, we have different aerofoils. This is our symmetrical aerofoil. If we cut like this, then we will get two equal parts. Okay, then these two equal part is been renamed again. That is the symmetrical aerofoil and unsymmetrical aerofoil. So here this case will come under symmetrical aerofoil case, and this one unsymmetrical. Okay, because in this part, if I cut, then see here we can able to see the two equal parts, the 50% upper surface and 50% lower surface. Okay, and that is shown here. Okay, and again this 50% aerofoil again renamed, that is the unsymmetrical aerofoil. Okay, so here airfoil. So here, the maximum all our air components are in this airfoil shape. Okay, because the drag will be less in this kind of airfoil shape. Okay, so here we have different air components. Okay, and I told you about the type of airfoil. Okay, that is symmetrical and symmetrical airfoil. Okay, so this is case for asymmetrical, symmetrical and asymmetrical, which means here if we take okay, if I cut along like this, okay, from leading edge to trailing edge, okay, in this case the chord line and the camber line that will coincide one above the other. Okay, then we can able to see the upper surface like this and the lower surface like this. Okay, so that will come under the symmetrical case because after cutting this part, okay, we'll got two equal parts. This two equal parts they are equal. So that's why we are calling it a symmetrical case airfoil and asymmetrical in the sense here if you cut from leading edge to trailing edge, then you will not get the equal parts. Okay, upper surface part will be 58% or 60% or 70% will get upper surface content. But and similarly, if we take this part lower surface, then that will be just 30% or 40%. Okay, which means that will come under the unsymmetrical case. So in this unsymmetrical case or asymmetrical case, okay, the aerofoil will look like this. Okay, so here aerofoil is a shape used for your aeroplane wing that consists of curved top surface and the flat bottom surface. See here, we have upper surface completely curved and the bottom surface completely flat. So that's why we are telling the aerofoil shape that we use for our aeroplane components or especially the wing. Okay, which consists of a curved top surface and the flat bottom surface. So it is designed to increase the lift production by changing the speed at which you move with some speed. Okay. So even this aerofoil, what we have the shape of body. Okay. So over this uh, shape, air will flow. Okay. Yeah. Suppose we have the aerofoil shape. Okay. So in this case, what will happen? Okay. Suppose you are flowing air from this end. Okay. And as you know, air will flow over upper surface and lower surface like this direction of the fluid that is the air. Okay, so here the air travels over the top of the wing. And you know, if I can extrude this, then you can able to see this is our wing only. Okay, so air will flow. This air, whatever we have or whatever I have shown here. Okay, this air will travel over the top of the wing. Okay, farther and faster as compared to the lower surface. Okay, because the curve shape. Okay, thus the faster air will move. Because of this, what will happen? The pressure will be less over the upper surface, and in this lower case, what will happen? Air will flow slowly. That's why pressure is high. below the wing. Okay, so if I give an example, then suppose you have went to bank, okay, and the cashier is working very slowly. Okay, many people are standing in a line. Okay, if he is working very slowly, which means pressure will create here more. Okay, in this area, pressure will create more because the work process is very slow. Okay, if this person, if he work very fastly, then here there will be no any pressure in this area, which means people will move fastly, right? And they will exit, they will go out. Okay, in this room or in this bank, okay, there will be no any pressure. So similarly, if your air is moving very fastly over the upper surface, then there will be less pressure. Okay, if this person will work very fastly, then there will be no any pressure in this area. So people will move and they will complete their work and they will move, they will exit. Okay, which means there will be no any pressure. Similarly, here for the upper surface, if air is moving very fastly, okay, then pressure will be low. Because of the low pressure, and what will happen, suction will create over the upper surface. Suction force in the sense somebody sucking, okay, air is giving such kind of energy to the wing, especially over the upper surface. That energy known as the suction energy or suction force. Okay, suction force will create. And similarly here, here or here below the wing, will get high pressure. So because of the pressure difference, we know the lift will generate, right? So here, because of because of the pressure difference will happen, overall resultant will get, that is the lift. And we know because of the air, we will get one more component, that is the drag component D. Okay, so here we will do alterations in our aerofoil. Okay, symmetrical aerofoil, if we take, then we will not get that much of pressure difference, which means resultant lift will not get that much as compared to the unsymmetrical. So that's why we prefer unsymmetrical, just to increase the lift coefficient CL. Okay, we know lift is equals to 1 by 2 rho b square s and CL. So this lift coefficient, okay, what we will get, and the wing area, velocity of the air, density, at what atmosphere you are flying your aircraft. Okay, which means overall lift is directly proportional to these all parameters. The density, which means at what altitude you are flying your aircraft. Okay, and the velocity and the wing area and lift coefficient. So these all parameters will play an important role. Okay, for overall resultant lift. So here, yeah. So here, as I told, we have to verify that is symmetrical and unsymmetrical. Okay. So symmetrical in the sense no lift at 0 degree angle of attack. Okay. What will happen in this case if you have a wing with symmetrical like this? Okay. So in this case, what will happen? There will be no any lift at 0 degree angle of attack. I'll take along x angle of attack alpha. Okay. And along y, I'll take lift coefficient CM. So in this case, what will happen? Okay, there will be no any lift at 0 degree angle of attack. So here I'll take 0 degree. Here I'll call 5 degree, 10 degree, 15, 20, 25, like this. Okay, in this case, okay, which means in this symmetrical case, at 0 degree angle of attack, there is no any lift. Okay, which means the curve will be like this. Whereas in unsymmetrical case, because of the more curvature in the camber, what will happen? There will be some amount of lift coefficient. Okay, some amount of lift coefficient at 0 degree angle of attack. Okay, lift will create even at a small angle of attack. Which means the graph will be like this. Okay. So this angle of attack alpha and the CL. So that's why we will go for different aerofoil section. Okay. So these all things already told you. Just I wanted to show. That's why I have included this figure. Okay. The nomenclature which I have already discussed in the previous class. Suppose you have the aircraft like this. Okay. So we will place our aerofoils. Okay. To design the complete wing model. Okay. So to design the wing, we need the aerofoil. Okay, and that's why it's very important to know about the aerofoil nomenclatures. So here we have the aerofoil nomenclatures. Okay, the camber of upper surface and the camber of lower surface. So here we can able to see the upper surface and lower surface. So why we have the cut section? Just to take out the unwanted parts, because as we know we have to even see the weight component, right? That's why if we remove this cutout and all, we can reduce our overall aircraft weight. So that's why cutout will be done. The part which is not required. See, only we need the shape. That's why we are placing the shape, aerofoil related shapes. Okay, side by side, and we will design completely model. Here we have the timber line, the ring gauge, chord line, and the ring gauge. Similarly, shown in the slide. Okay, the 2D view. This is our leading edge. Okay, this is our leading edge, and this one is our trailing edge. Okay, and see, this aerofoil is not a symmetrical aerofoil; it's an unsymmetrical aerofoil because here we have the camber. Some amount of camber is there. Okay, which means the chord line and the camber line is not coincide one above other. Right? Instead of that, we have some distance. It's a gap between the chord line and the camber line. That gap is known as the camber thickness. Okay, so that's why we are calling this aerofoil as an unsymmetrical aerofoil or asymmetrical aerofoil because of the camber. Okay, so the overall thickness will be measured like this: upper surface and the lower surface. Okay. So these are the things I will discuss. So just I will know. So these things you have to remember that symmetrical aerofoil and unsymmetrical, whatever I told. So symmetrical aerofoil, the chord line and the camber line will collide one over the other. Okay, and in unsymmetrical case or asymmetrical case, you get the gap between the chord line and main camber line. That gap we will call generally as a camber, thickness of the camber. Okay, so a symmetrical case that is less stable, more expensive, and more lift will generate. This kind of aerofoil will generate more lift as compared to the symmetrical aerofoil because of the camber and because of the more curvature over the upper surface. Okay, so that's why the asymmetrical aerofoil or unsymmetrical aerofoil will generate more lift as compared to the symmetrical aerofoil, and this asymmetrical aerofoil is less stable and more expensive because the design is not as simple as the symmetrical. That's why it's a little bit uh, more expensive. Okay, and less stable. And this one is less expensive, more stable. Okay, like this we have different aerofoil. Okay, so based on this scenario, okay, based on these differences, we can design different type of aerofoils. And already we have seen, and already in our real life we have this all different aerofoils. With respect to these different aerofoils, different aircraft has been designed, right? Like a fighter jet, commercial aeroplane, okay, UAVs, quadcopter, okay, rotorcraft, waves, okay, and many other aircrafts what we have. Okay, sonic aircraft, subsonic aircraft, supersonic, hypersonic aircraft, like that. Different based on the speed, we have different aerofoils. As per our requirement, we will choose that aerofoil and we will use for design purpose, right? So here, see earlier aerofoil, later aerofoil, and we got the aerofoil for subsonic case. Okay, that is laminar flow aerofoil, clairvoyant aerofoil. Okay, and for supersonic. Okay, which means if you're designing any aircraft, okay, which will be going with some speed that is the supersonic speed, then we have to do alterations with our fuselage, with our aerofoil design. Okay, and the shape we have to maintain like this. Okay, for supersonics. Okay, and for hypersonic, subsonic, like this for different aircraft. Okay, the wing design, if you see, that is different because of the different aerofoil sections. Okay, so here, yeah, one more point I have to tell. Yeah, here, see, the aerofoil. What we have is aerofoils, different, whatever I have shown. Okay, these aerofoils that will affect the cruise speed and also while doing takeoff and landing time. Okay, uh, okay, let me start my laptop just a minute. Yeah, okay, yeah. So what I was saying, aerofoil, I can say this aerofoil is like a heart for your combat aircraft. Okay, or it is the heart of your aeroplane. So that's why this aerofoil what will have this aerofoil, it will affect the cruise speed, takeoff and landing distance, stall speed, and the handling qualities. So overall, your aerodynamic efficiency during all phases from takeoff to landing. So this all aerodynamic efficiency will depend upon the aerofoil shape. Okay. So here, okay, I have shown one basic model. So by designing the basic model, there we have placed the aerofoil, that is the aerofoil NACA 2421. So this aerofoil I have placed, and even that aerofoil I have shown. Okay, and nomenclature also discussed. Just once recap these all nomenclatures, because next what I'll be telling, that is very important, because here see, not only 4-digit aerofoil we have, we also even have the 5-digit and 6-digit airfoils. Okay, so we'll move to that now. So this is the gauge radius, maximum thickness from upper surface to lower surface. The distance will be of the maximum thickness, mean camber line. So this aerofoil, what we can able to see, this aerofoil easily we can see, easily we can tell by seeing to this aircraft. By seeing to this aerofoil, we can say that this aerofoil is the asymmetrical aerofoil, because we have the thickness, maximum camber thickness. Okay, the mean camber line and the chord line, they are not collide one above the other. There is a some amount of distance, the gap. That gap is known as the maximum camber gap or maximum camber thickness. And the distance from leading edge to trailing edge, okay, that is known as the chord, generally called C. And the straight line what we have from leading edge to trailing edge, that is the chord line. And other things already discussed. So that I will, yeah. So let's see. So here we have the green line, that is the camber mean line. This one, okay. And we have, that is the chord line. See, there is a difference between the chord line and the mean line. If I cut along this mean line, then I can able to see, and I can easily get the two equal parts after cutting along this mean camber line. Okay, if I cut along this chord line, okay, then I'll get two equal parts, but the upper surface size and the dimension overall area will be more as compared to the lower surface. Okay, so that is a major difference between the chord line and the mean camber line. Chord line, that is sorry, mean camber line, that is the equidistance line, and the chord line, that is just a straight line from the leading edge to the leading edge. That's it. Okay, and here we have the leading edge radius, and this aerofoil. What we have, this aerofoil is the asymmetrical aerofoil because there is a gap between the mean camber line and the chord line. Okay, so that's why we can easily say the aerofoil what we have, this is the asymmetrical aerofoil. Okay, and here see we have x and y coordinate for the profile geometry. Okay, so chord overall x axis and y axis line on that leading edge. So here you can non-dimensionalize your chord, okay, with respect to x and y coordinate, and you can uh, measure your maximum thickness, maximum camber, location of your maximum camber from leading edge. Okay, so based on this, even I have shown this thing, right, while designing our NACA 2421 aerofoil. Okay, so this profile line what we have, the first one, that is the chord, and the second line what we have, that is the camber, and the third line, that is the length. Okay, fourth one is the midline. So here the shape of your NACA aerofoil is described using a series of digits following the word, that is NACA. Okay, so example I have shown here, that is NACA 2421. Okay, so if you take any shape, okay, any kind of aerofoil shape, okay, the shape of your NACA aerofoil, that will be described using a series of digits. Okay, like this 2421 or 0012 or 1428. So like this, you'll be getting digit following the word, that is NACA. Okay, National Advisory Committee of Aeronautics. Okay, and following number, the digit. So this four digit what we have, this four digit, in this four digit first digit, that will tell about the maximum camber. Okay, that is 2% of 2D aerofoil. Okay, and second digit, that will give you idea about the location of your maximum camber from the leading edge. So see, from leading edge, the location of your camber is 40%. That is 0.40 meter. Okay. Suppose overall length of your aerofoil from leading edge to trailing edge, that is the chord length, suppose 1 meter. Okay, so from that 1 meter, 0.4 meter, okay, from leading edge to 0.4 meter. Okay, so that will give you idea about the location of the camber. It means your camber will be located from leading edge to 0.4 meter. Okay, in that range, okay, from leading edge to 0.4 meter, in that range or in that distance, you will get or you can able to find the location of your maximum timber. Okay, so like this only, uh, we have for 5 series and 6 series aerofoils. Okay, and last project I already told in last class. Okay, that what we have the last two digit that will give you idea about the maximum thickness, that is 21%. So that is in percentage. So if you convert percentage into a number, then that will be 0.21 meter. Okay, 21 divided by 100, that is 0.21 meter. So here I have shown for different series, 4 series, 5 series and 6 series, that is 4 digit, 5 digit and 6 digit airfoils. Okay, so here first we'll see about the Naka 4 digit series airfoil. Okay, the first digit I will told you, okay, specifies the maximum camber in percentage of chord, and second digit. Okay, so I have two different examples. So here we have first digit 2. So this first digit 2 number 2 what we have, that will give you idea about the maximum camber in percentage of chord, and the second digit, that is 4. Okay, so the second digit 4, that indicates the position of your maximum camber in the 10th of the chord, and last two digit that provide maximum thickness of aerofoil in percentage of chord. So here camber of 2% located 40% back from aerofoil leading edge, that is 0.4 chord, 0.4 times of chord, and aerofoil has a maximum thickness of 15% of chord, that is 0.15. Okay, suppose if you consider the overall coordinate as 1 meter, then 15% in the sense 0.15 times of chord. Okay, so this one is for 4 digit series, and next we have the Naka 5 digit series aerofoil. Okay, so here Naka 5 digit aerofoil, you make it like this: 23012 or 12015. Okay, so if you see any such numbers, that is Naka, after that any 5 digit number, then that indicates first digit what we have, the 2, that will indicates the specify, or that will specify the design diff coefficient in 10th when multiplied by the 2 by 3. Okay, and second digit what we have 3 and 2. Okay, that indicates the position of your maximum timber in percentage of chord when multiplied by 1 by 2. Okay, and last two digit same, that is that will give idea for the maximum thickness of an aerofoil in percentage of chord. So 23012, in the sense aerofoil has design diff coefficient of 0.3. Okay, and location of maximum timber is at 15% of chord from aerofoil linkage, and last two digit, there is a maximum thickness of 12% of chord, that is 0.12 times of chord C. Similarly, for 6 digit, so 6 digit aerofoil, that is Naka, some 2 digit, and after gap you may get 3 number. Okay, so if you see any such aerofoils with the 6 digit series, then that first digit what we have the 6. Okay, that indicates the series design. Okay, and the second digit indicates the location of minimum pressure in 10th of the chord, and third digit what we have specifies the design coefficient in 10th, and last two digit provides the maximum thickness of airfoil in percentage of cord. So this is all about today's theory. Okay. So whatever I have discussed, this theory part one. Okay. So same thing tomorrow I'll tell. Okay, like this. So here default we have airfoil. I'll check the airfoil, that is 4 series 0012, which means Naka 4 series airfoil we got, that is default airfoil, that's Naka 4 series airfoil with thickness to chord ratio 10%, camber 0, and location of camber 20% from leading edge. Okay, so if I see this, then the airfoil will look like this. Okay, and if I change the airfoil, okay, and do some changes and change thickness to chord. Okay, so and change the camber. See, from symmetrical to unsymmetrical, right? Like this, because I increase the camber and thickness to chord. So see, symmetrical aerofoil were converted to unsymmetrical because there is a movement of camber, right? First digit, second digit, third and fourth digit. Last two digit that will give idea about the maximum thickness of an aerofoil. And this second digit what we have, that will give you idea about the location of the camber. And first digit what we have, that will give you idea about the camber thickness. Okay. So like this, we can design the aerofoil, which means we can design complete our wing by placing this kind of aerofoils. Okay, as per your requirement, like 4 series, 5 series, and other series aerofoils. Okay, and you can increase your lift coefficient, means overall lift coefficient CL. So this is all about today's topic. I'll continue tomorrow. It's already 6:40. Okay then. Bye to all. Thank you for listening.
Thank you, sir. Thank you.
Okay, okay, thank you. I'll end then.